Hi, hello everyone. This is DJ again. Today I am going to explain about the wave propagation in free space and good conductor in subject of electromagnetic waves and transmission line. Wave propagation from free space to conductors. Understanding how electromagnetic waves behave in different media is fundamental to modern communications, power transmission, and countless technological applications. This presentation explores the journey of EM waves from the ideal vacuum of free space into the complex environment of conducting materials. This slide, I'm going to explain about the Maxwell equation. James Clerk Maxwell four equations from the cornerstone of classical electromagnetism, describing how electrical and magnetic fields are generated, interact, and propagate through space and time. There are four Maxwell equations: Gauss law for electricity, Gauss law for magnetism, Faraday's laws, Ampere's Maxwell law. Gauss law for electricity is del dot E is equals to rho by epsilon naught. Electric field divergence relates to charge density. Gauss law for magnetism is del dot B is equals to 0. Magnetic monopoles does not exist. Faraday's law is del cross E is equals to minus dou B by dou T. Changing magnetic fields induce electric fields. Ampere's law is del cross B is equals to mu naught J plus mu naught into epsilon naught into dou E by dou T. Currents and changing electric create magnetic fields. These four elegant equations unfold unified electricity, magnetism, and optics, predicting the existing of electromagnetic waves. What is free space? The free space is known as the ideal medium. Free space represents the simplest propagation medium for electromagnetic waves, characterized by two fundamental constants epsilon naught and mu naught. Epsilon naught is also known as the permittivity of free space. It has the approximate value of 8.885 into 10 power minus 12 force per meters, and mu naught is the permeability of free space, that is approximately equal to 4 pi into 10 power minus 7 Henry per meters. In this free space, there is absence of charges. That implies no free charges exist, eliminating source items in Gauss law. There is also no currents, no free currents flow, simplifying the Ampere's Maxwell law. It is a linear medium. Electric and magnetic fields that relate directly to sources without material response. The absence of charges and currents dramatically simplifies Maxwell equations, allowing electromagnetic waves to propagate without attenuation or distortion. Wave equation in free space. Starting from Maxwell's equations in free space and applying vector calculus identities, we derive the wave equations that governs electromagnetic propagation is shown in the figure. This elegant equation reveals that electromagnetic disturbances propagate as waves at a constant speed determined solely by properties of free space. The speed c represents the speed of light in vacuum, one of the most fundamental constants in physics. This derivation fulfills light with electromagnetic phenomena, demonstrating that visible light, radio waves, X-rays, and gamma rays are all manifestations of electromagnetic radiation. Slide, I am going to explain about the characteristics of EMFs in free space. Transverse nature. Electric field and magnetic field are perpendicular to each other until the direction of propagation, forming a right-handed orthogonal system. Second is in-phase oscillation. Both fields oscillate in perfect synchronization, reaching maximum, minimum, and zero values simultaneously at any point in space. Energy propagation. The Poynting vector S is equal to E into H. E cross H indicates the direction and magnitude of electromagnetic energy flow, always parallel to the propagation direction. And the fourth one is frequency wavelength relation. Introducing material media. When electromagnetic waves enter material media, they interact with the charged particles constituting the material. These interactions fundamentally alter wave propagation through three main mechanisms. First one is conduction, second one is polarization, and third one is magnetization. Conduction means the free charges and move under electric field influence, creating currents that dissipate wave energy as heat. In polarization, bound charges displace relative to each other. creating electric dipoles that modify the effective permittivity. In magnetism, atomic magnetic moments align with electric external fields, altering the effective permeability of the material. The conductors, the flow of charge. Conducting materials, particularly metals, contain abundant free electrons that can move easily through the atomic lattice when subjected to an electric field. This property defines their high conductivity, measured in Siemens per meter. Free electron gas, ohmic behavior, energy dissipation. The relationship J is equal to sigma is incorporated directly into Maxwell equations, replacing the simple vacuum case when J is equal to 0. This seemingly small modification profoundly affects wave propagation, introducing damping and attenuation. Maxwell equations in conducting media. The key difference between vacuum and conducting media appears in Ampere's Maxwell law, where conduction current must be included alongside displacement current. First one is combined Maxwell equation, second one is obtained telegram equation, and the third one is complex wave number. Plane waves in good conductors. Conductor is classified as good when its conductivity dominates over displacement current. And good conductors like copper at radio frequencies, the wave experiences so severe attenuation, the complex wave number becomes as shown in the figure. The real part beta determines phase propagation while the imaginary part alpha governs exponential decay. Both are equal in magnitude for good conductors, leading to rapid amplitude reduction with distance. Slide, I'm going to explain about the attenuation and skin depth. A complex wave number produces exponential decay of wave amplitude with depth into the conductor. 37% characteristic reduction, delta skin depth formula, frequency dependence. High frequency yields smaller skin depth, concentrating current near surface. The skin depth represents the characteristic distance over which wave amplitude decays to 37% of its surface value. For copper at 60 Hz, delta is approximately 8.5 mm, while at 1 MHz, delta is approximately 0.66 mm. This phenomenon is called skin effect, causes high frequency currents to flow primarily near to the conductor surface, increasing effective resistance. Thank you. Thank you everyone for listening this class.